Hello, my name is Braden Shaw, and today I will be presenting on fundamental concepts that play a major role in our solar system. I will also we'll be going and talking over today angular momentum. Throughout this presentation, I'll walk you through what the solar system is, how rotation and revolution work, what angular momentum actually means, and the important equations behind it. And finally, how conservation of angular momentum shapes the behavior of planets, moons, and even the Earth itself. Let's begin. And if I hadn't stated before, my name is Brian Shaw. I'm from uh, Dr. Store's 1230 University Physics course, and this is the AI or whatever video assignment. Now let's begin. So first, an overview of the presentation. Here's a roadmap of today's presentation. First, I'll give a quick overview of the solar system, then I'll explain the rotation and revolution and how they relate to mo relate to motion in space. Next, I'll introduce the basics of angular momentum, followed by the core equations and what they represent. After that, we'll take a look at examples within the solar system, including the Earth, the Moon, and planetary orbits. And finally, I'll wrap up with the summary to highlight the key ideas. By the end, you should have a strong understanding of of how our how angular momentum keeps our solar system stable and predictable. So next slide, the solar system overview. To start, the solar system is a gravitationally bound system made up of a variety of astronomical bodies. At the center, at the center is the sun, which holds about 99.8% of the entire system's mass. Surrounding the sun are eight planets, ranging from Mercury, the closest, all the way out to Neptune. In addition, the solar system includes moons, asteroids, comets, and dwarf planets. All these objects are moving according to the gravitational force and Newton's laws of motion. Understanding this structure is important because every object in the solar system has angular momentum, and the interactions between all of them are governed by the principles we'll talk about today. Next slide. Our next topic will be rotation and revolution. Now let's talk about these two essential types of motion, rotation and revolution. Rotation refers to the spinning of a body around its internal axis. A familiar example is Earth rotating once every roughly 24 hours, which gives us day and night. Revolution, on the other hand, is an object's orbital motion around another body. For example, this mean for the Earth, this means completing one full orbit around the sun in about 365 days, which gives us a year. Both rotation and revolution contribute to um, contribute to an object's orbital momentum, how fast something is spins, and how far it is from its axis. Um, Both of these play a major role in determining an object's overall um, orbital or angular momentum. All right, for the next slide. Now let's talk about basics of angular momentum. Angular momentum is essentially the rotational equivalent of linear momentum. It describes an object's tendencies to keep spinning or moving around in a curved path or moving in a curved path. It depends on three things: the object's mass, its velocity, and its position relative to an axis. There are two there are two major forms of angular momentum. The first is orbital angular momentum, which applies to objects moving in orbits, such as planets orbiting the sun. The second is spin angular momentum, which describes how objects rotate about their own axis, like the Earth spinning on its axis. Together, these two forms describe how objects move and interact in a system like ours. Next slide, slide 6. And angular momentum equations and vectors in vector form. Angular momentum can also be expressed using vector equations. For orbital angular momentum, it is defined using a cross product between the positions vector and the momentum of the object. This equation emphasizes two key ideas: how far the object is from the axis and how far it is moving, or how fast it is moving. Um, for rotating rigid bodies such as planets or solid objects, we use a different form involving the moment of inertia and angular velocity. The direction of angular momentum is determined by the right-hand rule, meaning in general, the larger the radius or the faster rotation, the greater the angular momentum. Now for slide 7, which is angular momentum in the solar system. Now let's look at angular momentum at the scale of the entire solar system. Interestingly, most of the solar system's angular momentum is not the sun, even though it contains almost all the mass. Instead, most of the angular momentum is stored in planets. Jupiter alone holds about 60% of the system's orbital angular momentum, mainly because of its huge mass and distance to the sun, or distance from the sun. The sun does not contribute to rotational momentum, but because it spins relatively slowly, its share is smaller. Um, the moons and smaller bodies like asteroids also contribute, but their amounts are very minor compared to planets, which are a lot bigger. And the next slide. Earth's angular momentum. Focusing especially on Earth, there are two main equations that describe its angular momentum. For example, such as Earth's orbit, angular momentum is given by the expression right there with L is equal to mvr. For Earth's rotation as a rigid body, angular momentum is described by L equals I omega, where I is the moment of inertia and omega is the angular velocity. Moment of inertia tells us how mass is distributed in relation to the axis, and angular velocity, or sorry, how the axis and angular velocity describes how fast the object is spinning. In simple terms, objects with larger radii or faster rotation have a greater angular momentum. That's why larger spinning planets can hold so much angular momentum. Now to the next slide. Um, Conservation of angular momentum. A key principle in physics is the conservation of angular momentum. This states that in an isolated system, angular momentum remains constant unless an external torque acts on the system. A common everyday example is an ice skater spinning. When they pull their arms inward, they reduce their moment of inertia, causing their spin rate to increase. In astronomy, this principle explains how larger structures form. Gas gas clouds collapse inward to gravity, and as they shrink, they spin faster. This is how stars and planetary systems begin. Um, it also helps explain why planets maintain stable orbital paths unless something external interferes. And so for the next slide, um, Earth-Moon dynamics and angular momentum. Now let's connect conservation of angular momentum to the Earth-Moon system. Earth's rotation is gradually slowing down because of the tidal interaction with the moon. As the Earth's rotation slows, angular momentum is transferred to the moon, causing the moon to slowly move away further, about 3.8 centimeters per year. Because of this transfer, Earth's day becomes slightly longer over time, increasing by about 1.7 milliseconds per century. Despite these changes, the Earth's moon system as a whole conserves angular momentum, which is why the overall structure remains stable. And for the next slide, angular momentum and planetary orbits. Angular momentum can also play a major role in planetary orbits. For example, Saturn's rings are shaped and maintained by the orbits by the distribution of angular momentum within the rings particles. Uh, Orbital resonance in resonance in Jupiter's moons, like the famous 1, 2, 4 resonance between Io, Europa, and Ganymede. Sorry if I butchered that. Are also governed by angular momentum interactions. On a larger scale, this principle explains why planets will follow a predictable path around the sun, as long as external forces do not significantly disrupt the system. Planets continue moving in a stable orbits thanks to the conservation of angular momentum. And now for our last slide. To summarize, the solar system is a dynamic structure governed by the principles of angular momentum. Both rotation and revolution play essential roles in how objects move. These equations, L equals RxVm and L equals I omega, help describe orbital and rotational angular momentum. Conservation of angular momentum keeps planetary orbits stable and explain long-term changes such as the Earth's slowly rotation and the moon's gradual drift outward. In short, angular momentum acts like the invisible hand that keeps the solar system organized, stable, and in constant motion. Thank you so much. And here are a list of my references from physics, Liber Text, Britannica, Copilot, and Isaac Science. I also did use a bit of ChatGPT to help format. And that is my presentation. Thank you so much.